our last topic is to finally talk about electrolytic cells. So just a reminder, these are non-spontaneous or non-thermodynamically favored reactions that occur when current is applied. And there are a number of applications for electrolytic cells. So one is that this is used in the production of H2 and O2 from H2O. It's also used to create pure metals. So we do often use things like pure sodium metal to do chemistry. I mean, you won't in Gen Chem lab for sure, because it's a little on the dangerous side. But, so we'll say Na solid, for example. The easiest way to find and handle sources of this would be from, a pretty safe, stable salt. So something like sodium chloride. And we can use this process, which is actually called electrolysis, to get pure sodium metal out of sodium chloride. And along the same lines, it's used for things like metal plating jewelry. So something like gold-plated earrings would be first very expensive if they were solid gold, but also things that are made out of gold are sometimes really soft, which makes it impractical for a piece of jewelry that won't get smooshed, I guess. So you can use a solid core that's also a little bit cheaper and then put a gold plating over the jewelry. So when you set up an electrolytic cell and you calculate a cell potential, what that cell potential tells you is the minimum voltage that must be applied for the reaction to go. And what we will do with electrolytic cells are usually just calculations using something called Faraday's law of electrolysis, which doesn't tell us anything that I think we haven't used before, because I feel like we've done these stoichiometry calculations with some half reactions, but this just puts some explicit words down letting you know that you can do these stoichiometry calculations with half reactions. So Faraday's law of electrolysis says the amount of product formed or reactant consumed by an electric current is stoichiometrically equivalent to the number of electrons supplied. All right. And the values that you will need, it's not really a value, but electrons are going to be used for stoichiometry conversions. So you're going to need a proper half reaction. You will need to remember that 1 amp is equal to 1 coulomb per second, because we'll usually talk about how long the current in amps is supplied. So you'll have a time period, and then you'll need Faraday's constant, which is just telling you that 1 mole of electrons carries a charge of 96485 coulombs. So what I'm going to do is pause this video, write out a quick practice problem, and then we'll step through some of these conversions. So our practice problem says gold can be plated out of solution by the reaction below, which I'll give you in a second. And the question is, what mass of gold is produced by a 25-minute flow of 5.5 amp current? And the reaction that we're going to look at is gold 3 plus, aqueous plus 3 electrons, turning into gold as a solid. All right. So we do have everything that we need here. We are asked for a mass of gold, so grams of gold. So, all right, let's just kind of step back incrementally. I know that I can get from moles to grams. So if I can figure out how many moles of gold I produce, then I can just go look up the molar mass of gold and get to the grams value. So what we just looked at with Faraday's law is kind of setting up that I can use this reaction in order to go from electrons to gold, right? I have a balanced half reaction. So 3 moles of electrons, for every 3 moles of electrons that I push through in this reaction, I should get 1 mole of gold, because those are the coefficients in my reaction. So if I can get moles of electrons, I should be able to get moles of gold. So the other information I have, so the only way that I can approach getting moles of electrons is with this information about the current. So I have amps and I have time. So I should be able to go from current in amps to charge in coulombs. Well, these aren't quite lined up, but that's fine. With the current and then changing my 25 minutes into seconds. And Faraday's constant will let me go from charge in coulombs to the number of moles of electrons. So this looks fantastic. So my 25 minutes, I need to get this into seconds, so 60 seconds in 1 minute. And if I then multiply that by the 5.5 coulombs per second, that'll tell me exactly how many coulombs of charge I've put across in that time period. I'm in coulombs, and I know that 1 mole of electrons has a charge of 96485 coulombs. So I'm in moles of electrons. For every 3 moles of electrons, I get 1 mole of gold. And if I go to the periodic table, gold has a molar mass of 196.97 grams per mole. So if I run this current for 25 minutes, I will get 5.6 grams of gold plated out.